Good morning, students. Let us start a new important concept in electrochemistry. So, what do we mean by electrochemistry? It's a branch of chemistry which deals with the conversion of chemical energy into electrical energy. We are going to see the important application of a number of chemical reactions in which the chemical energy is getting converted to electrical energy, and we will see how it has been made use of. And in detail, we are going to see what do we mean by electrode potential and how to determine the electrode potential using Nernst equation. So, what do we mean by electrode potential? Okay. So, what do we mean by electrode potential? See, every electrode, all of us know that electrode is nothing but when you take electrode, and electrode is nothing but it is a metal. Usually, the metals are good conductors of heat and electricity. So, a metal which is a good conductor can behave as a electrode, and electrode in the form of a metal strips or metal bars or metal rods can conduct electricity, and it differs with the metal to metal. Each metal has its own potential to conduct electricity, and that is known as electrode potential. Now, we go to the very important term that is known as single, single electrode potential. That is, we are going to see what do we mean by single electrode potential. Okay. Now, what is single electrode potential? It is defined as a tendency of an electrode either to lose electrons or gain electrons when it is in contact with its own solution. That is known as single electrode potential. Every metal or every electrode has its own capacity to lose electrons, and that is known as its oxidation potential. That is known as its oxidation potential. Okay. And this oxidation potential is attained by the loss of electrons. Similarly, every metal has its own capacity to accept electrons, and that is known as reduction potential. Okay. And the reduction potential is attained by the gain of one or more electrons. So, under electrode potential, we have seen what do we mean by single electrode potential? That is the tendency or capacity of an electrode either to lose electrons or gain electrons when it is in contact with its own solution. If it has a capacity to lose one or more electrons, it is known as its oxidation potential. Otherwise, if the metal has the capacity to gain electrons, one or more gain electrons, it is known as its reduction potential. The next one is, what do we mean by standard electrode potential? So now take down the term standard electrode potential. Now, what do you mean by standard electrode potential? The same definition gets repeated. It is a tendency of a metal electrode either to lose electrons or gain electrons when it is in contact with its own solution at STP or NTP. That is, we are using the term STP. Now, what is STP? Standard temperature and pressure. That is, you have to maintain the temperature 25 degrees Celsius, that is equal to 298 Kelvin, and the pressure is 1 atmospheric pressure. So when you carry out the reaction at 25 degrees Celsius and 1 atmosphere pressure, and if you measure the capacity of an electrode to measure, that is to lose or gain electrons, that is known as its standard electrode potential. Every metal has its own potential. It can be either an oxidation potential or a reduction potential. And when it is said to have oxidation potential, it has a tendency to lose electrons. When it is said to have a reduction potential, the same metal has the capacity to accept or gain one or more electrons. Now, what are the factors which influence the electrode potential? The first one is the nature of the electrode. Nature of an electrode. The second one is the concentration of an electrolyte, which it is in contact. Concentration of an electrolyte. And next one is temperature. And the last one is pH. So these are the important factors which decide the strength of the electrode potential of each metal possess. Now, how to determine the electrode potential? So we are going to see determination of electrode potential. You can also understand this in the term of single electrode potential. Okay. For this, for mathematical determination of electrode potential or single electrode potential, we are using the equation that is known as Nernst equation. So all of you in your 12th standard would have seen about the Nernst equation, how to derive the Nernst equation, and what is the application of Nernst equation. Every one of you must be aware of that one. It's one of the very important question under part B. So using Nernst equation, we can find out the electrode potential of the metal in terms. You can construct a cell with the help of the electrode potential, and also you can estimate the EMF of the cell. Okay. Let us begin with the derivation of Nernst equation. Now, consider a reduction reaction. So all of you know what do we mean by reduction reaction. It is nothing but acceptance of electrons, otherwise gain of electrons. Again, all of us know that the ions can only gain or accept electrons. So let us take a metal ion Mn plus, and it gains n electrons. It accepts n electrons and becomes M. Okay. It can be a reversible reaction also. So here the M is the product and Mn plus is the reactant. That is, the ion gains electrons to become a stable metal. Okay. Now, from the want of isotope, okay, I'm not going to the derivation of want of isotope. I'm going to the expression of want of isotope. We know that from the want of isotope, we know delta G is equal to delta G naught plus RT ln concentration of the product by concentration of the reactant. Okay. So let this be equation 1. This is known as a well-known want of isotherm, which gives the relation between the standard free energy change and the free energy change of the chemical reaction, which undergoes the reduction reaction. Okay. We also know that delta G is equal to minus NFE, where F is the Faraday current and E is the potential, electrical potential. Similarly, delta G naught is equal to minus NF E naught. Then the equation 1 will becomes minus NFE is equal to minus NFE naught plus RT ln concentration of the product by concentration of the reactant. Okay, so let this be equation 2. Okay. Now divide the equation 2 by minus NF. So what do you get? E is equal to E naught minus RT by NF ln concentration of the product by concentration of the reactant. E is equal to E naught minus RT by NF ln concentration of the product by concentration of the reactant. Now, we have taken that Mn plus n electron gives M. This is the equation we have considered as a standard electrode product. There is a standard reduction reaction. So there the product is M and the reactant is Mn plus. So therefore, we can write the equation as E is equal to E naught minus RT by ln, sorry, okay, E naught minus RT by NF ln, what is the product? It is M. And what is the reactant? It is Mn plus. So let it be equation 3. Okay. Now, let the activity of the metal be unity. Therefore, we assume that equal to 1. That is concentration of metal. Since it has the unit activity, we are taking it to be 1. So therefore, the equation 3 can be written as E is equal to E naught minus RT by NF ln 1 by Mn plus. Okay. Now, I'm going to convert this natural logarithm to log base 10. So it becomes E is equal to E naught minus 2.303 RT by NF log base 10 1 by Mn plus. Okay, let this be equation 4. Okay. The same thing can be written as E is equal to E naught minus 2.303. Now I'm taking the R is a universal gas constant. Since we know the value of R, I'm substituting it to be 8.314. And temperature T is nothing but 298 because the reaction takes place at STP. And N, number of electrons that has been lost or gained. And the Faraday current is 96,500 coulombs. It becomes log 1 by Mn plus. Now, when you simplify, we are getting it to be E naught minus 0.0591 by N log 1 by Mn plus. Okay. And I'm bringing this Mn plus from the denominator to the numerator so that the sign becomes plus. So E naught plus 0.0591 by N log base 10 Mn plus. Equation 5. So now this is known as a Nernst equation for reduction potential. This is the Nernst equation for reduction potential. Similarly, we can write E is equal to E oxidation is equal to E naught reduction E naught reduction minus 0.059 by N log Mn plus. So equation 6 is the Nernst equation for oxidation potential. So students, I think I have derived the Nernst equation in a much simpler way so that all of you would have understood and you can easily practice and you can appreciate the derivation as well as use of Nernst equation to determine mathematically the single electrode potential. Now, after deriving the Nernst equation, we must know its applications. What are the applications of Nernst equation? The first one is you can calculate the electrode potential. Okay, so you can determine the electrode potential, whether it is a oxidation potential or reduction potential, anything it may be, you can calculate the electrode potential of the given metal. Okay, and the second one is you can construct a series which is known as EMF series. Okay, EMF series, otherwise electrochemical series. It is a arrangement of electrodes in the increasing order of their reduction potential as we move from top to bottom with respect to hydrogen as a standard element, otherwise standard hydrogen electrode as a reference electrode. Okay, and that series is known as electrochemical series, and it has a number of applications. To construct the electrochemical series, they make use of the Nernst equation to determine the single electrode potential of the various elements. And the next one is you can find out the extent of corrosion that every metal is subjected to. That is, you know that the metals are generally heteropositive, but among the metals, some are corrosive in nature and some are non-corrosive in nature. Now, how can you determine whether a metal can be easily corroded? A metal which can undergo oxidation can be easily corroded, and metal which undergoes reduction is usually not corroded. Similarly, you can go for the choice of the anode and the cathode if you know its electrode potential that is determined mathematically using a Nernst equation. Okay, that is a metal which undergoes oxidation generally act as the anode, and a metal or any element which generally undergoes reduction act as a cathode. Okay, so these are the general application of EMF series. So again, I'm repeating, it's one of the important 8-mark question. That is a part B question. Just go through again and again and thorough. Okay, be thorough with it. Thank you.